You know that feeling when you look at an algebra problem and it feels like you're trying to read a completely foreign language? Well, if that's you, you are in the right place. Today we are going to pull back the curtain on one of the most important ideas in all of math, functions. So let's get right into it. So what we're doing here is taking a lesson straight out of a college algebra course. The plan is to give you a full, comprehensive walkthrough. We're not going to skip any steps. We'll break down every single definition and example from this lesson, so by the end, you'll have a really solid, deep understanding of this stuff. And here's the game plan for how we'll get there. We're going to start with the absolute basics, relations versus functions. Then we'll figure out how to test for them. After that, we'll decode that special notation they use, get our hands dirty actually using functions, and finally, we'll see how it all comes together on a graph. All right, let's dive right into section 1, the foundation. You can't build a house on shaky ground, right? Same idea here. We can't really get functions until we first understand what a relation is. So let's start at the very beginning.
So what in the world is a relation? Honestly, it's simpler than it sounds. It's just a set of ordered pairs. Any rule that takes an input from one group of numbers, we call that the domain, and connects it to an output in another group, we call that the range. Look here, the input -1 is paired with the output -2. -10 is paired with -7. It's really just a pairing of numbers. That's it. Now here's where things get really specific. A function, well, a function is a special, much more reliable kind of relation. It follows one single critical rule. Every input can only have one and only one output. Think of it like a perfect machine. You put something in, you know exactly what's going to come out. Every single time. No guesswork, no surprises.
Okay, so that brings us to section 2, the test. Now that we know the big rule, how do we actually check if a relation is playing by it? How do we spot a real function out there in the math world?
Well, one way is to just look at the raw data. In this first example, see that input 3? It's paired with 6. But wait, it's also paired with 5. That's the red flag. That's the violation. One input, two different outputs. So that first relation is not a function. But if you look at the second one, every input has its own unique output. That one's good to go. It's a function.
Now, when you're looking at a graph, there's a super easy trick for this. It's called the vertical line test. And it's a wonderfully simple but really powerful visual tool. The rule is this: if you can draw a vertical line anywhere on the graph and it touches the curve more than once, it is not a function.
Let's actually try it out on these examples. Look at the top left graph. Whoop! A vertical line hits it twice. Fails the test. The oval on the top right fails again. And that sideways parabola on the bottom right, it also fails. Why? Because in every single one of those cases, a vertical line hitting 2 points means that one x value, our input, has two different y values, our outputs, and that's the one rule a function can't break. But now, look at the S-shaped curve on the bottom left. No matter where you draw a vertical line, it only ever crosses the graph one time. That one passes the test. It's a function.
Okay, section 3, the language. This is where we learn to read and write like a mathematician. I know it can look a little intimidating at first, but it's just a really precise way to communicate ideas. Let's break it down.
This right here is the basic grammar. We read y equals f of x as y equals f of x. In this sentence, x is our input, the independent variable. F is just the name of our function. Think of it as the name of our machine, like a Cuisinart or a Black & Decker. And y is the output, the result that pops out after the machine does its job.
And this is so important. This notation isn't just a bunch of abstract symbols. It can tell a real story. Let's say our function f tells us the number of police officers in a town in any given year. Well then, f of 2005 equals 300 is a complete sentence. It means when the input was the year 2005, the output was 300 police officers. See? It's a language. Section 4. The mechanics. All right, now that we can read the language, it's time to actually use it. And there are really two main things we do with functions: evaluating and solving. You can think about this as going in two different directions. Evaluating is the forward direction. You're given an input, an x, and you run it through the function to find the output, the f of x. Solving is working backward. You're given the output, and you have to figure out what input must have gone in to get that result. And please remember this note. F of x does not mean f times x. It is not multiplication. It's just notation. This works just the same with a data table. If I ask you to evaluate f of 5, we just find the input 5 in that top row and look down to see its output is 0. Simple.
Now, to solve f of x equals 2, we work backward. We find the output 2 in the bottom row and look up to see what inputs get us there. And in this case, it looks like both 0 and 3 give us an output of 2, and that's totally fine for a function, remember? Different inputs can go to the same output.
When you have an equation, evaluating is pretty direct. To evaluate h of 5 for this function, you just replace every single p you see with the number 5. It's just a substitution. So we get 5 squared plus 2 times 5 minus 3. Do the math, that's 25 plus 10 minus 3, which gives us a final answer of 32.
And solving, again, is just working in reverse. To solve g of m equals 2, we take the guts of the function, that's square root of m minus 4, and we set it equal to 2. From there, it's just plain old algebra. We square both sides to kill the square root, then we add 4 to both sides to get m all by itself, and we find out that m equals 8.
Now, sometimes solving is a bit more involved, like with a quadratic function here. To solve for an output of negative 30, our first step is to set the whole equation equal to negative 30. Step 2, we have to rearrange it so it equals 0. That's key for solving quadratics, so we add 30 to both sides. Step 3 can be tricky. We have to factor the expression. In this case, it factors into 4x minus 5 times x minus 6. Now, if two things multiply to be 0, one of them has to be 0. That's our final step. We solve each of those little pieces for x, and we find our two possible inputs, 5/4 and 6.
And that brings us to our final section, section 5, the visual. This is where we'll see how evaluating and solving actually look on a graph, tying all these ideas together in one picture.
This graph shows it all perfectly. To evaluate f of 2, you start on the ground, the horizontal x-axis, at the number 2. You go up to the curve and then look over to the side, to the vertical y-axis to find the output. It's 1. Now, to solve f of x equals 4, you go in the other direction. You start on the side, the vertical y-axis, at the number 4. You go across until you hit the graph, and then you look down to the x-axis to find your inputs. And look, it hits in two different places, at about -1 and at 3.
So there you have it. That's the complete toolkit for the basics of functions. You know what they are, how to spot them, how to read and write their language, and how to use them with tables, equations, and graphs. The real question is, now that you have these powerful tools, what's the next thing you can do with them?